Hello everyone, I'm Alvaro Rojas Arriagada. I'm going to tell you about stellar populations in the galactic bulge through the eyes of recent spectroscopic surveys. Over the last 1.5 decades or so, we have learned that the Milky Way bulge is a quite complex region of our galaxy. And this understanding has been driven by the massive observed datasets, photometric, astrometric, and especially spectroscopic surveys. So all of them have provided a detailed sampling of the resolved stellar populations living in different components of the Milky Way, and in particular in the bulge. And all of them are providing or have provided a very detailed sampling of the properties of the stars in all those components, and in particular in the bulge. But they require an expensive sample of large sky regions. We need to observe star by star, and that's expensive in telescope time. So we need that because we want a detailed sampling of structures such as the bulge. We want also a statistical sampling, so because we want to assess for the detailed distribution of properties and eventually the relation between them. So this kind of extensive observational effort has been performed with a lot of detail in the central part of the Milky Way, the region of the bulge, which before I mark here with a red box in this all sky image from Tomas. And here I'm marking, displaying with an optical image. So as we can see here, a lot of surveys over the 1.5 last decade have sampled stars in this region with optical spectroscopy. So much of our recent progress has been based on the analysis of optical spectroscopic samples. Here we have datasets from the Gaia ISO survey, Argos, and Gibbs, so color code accordingly. And the size of each symbol represents the field of view of each of those surveys. As you can see, they have avoided this region close to the midplane where the high extinction levels are impeding observations in the optical. But in the last year, some near-infrared spectroscopic surveys have been used to sample the region in that previously avoided part of the bulge. And this is because near-infrared wavelengths can pierce through the dust, so allow us to sample stars in the bulge are at those large distance at high extinction levels. So in particular here, I'm showing you the path of apogee fields, apogee sample fields, which as the case of optical spectroscopic surveys has been sampling bulge giants with the spectroscopy. So in this case, providing samples of bulge giants with high resolution and high signal-to-noise spectra, so allowing us to go beyond the parametrization of fundamental parameters, but going also to individual abundances, and granted also radial velocities, for example. So we have learned many things with those surveys, and in the following minutes, I would like to give an overview of the different things we have learned about the stellar populations in the galactic bulge using data from optical and near-infrared surveys. So here we start with metallicity, and you have here several fields coming from an optical survey. So this is the Gaia ISO survey from two papers of 2014 and 2017, where the distribution of the different panels is corresponding to a spatial distribution in galactic longitude and galactic latitude here. So fields which are close to the midplane are here, and fields which are far from the midplane here. So the first thing you can see here is that in all cases, the metallicity distribution function of bulge stars looks complex. In particular, it has been able to decompose them using a Gaussian mixture analysis using two components. So the first thing that we can see here is that there is a bimodality which emphasize or start revealing kind of underlying complexity. And you can see here that while the position of the components seems to be fixed in metallicity, if you compare the different fields, what changed from field to field, and in particular from far to close to the midplane, is the proportion between metal-rich and metal-poor stars. So what we see overall is that when we go close to the midplane, we see a larger proportion of metal-rich stars than when we go far from the midplane, where we see a large proportion of metal-poor stars. So this has been confirmed also by the results of other optical surveys, such as the GIF survey. So they provide a complementary picture in the sense that we have two components where metal-rich stars dominate close to the midplane. So this tells us immediately about an eventual different spatial distribution of whatever is being traced by metal-rich and metal-poor stars, in the sense that metal-rich stars are concentrated towards the midplane. The picture has been a bit complicated or complemented by the analysis of more recent spectroscopic data sets from near-infrared surveys. So here I'm showing you a sky map, so galactic longitude versus galactic latitude, and here color-coded the mean metallicity of sample of stars from the Apogee survey data release 16. So as you can see here in this qualitative map, overall we see that metal-rich stars dominate close to the galactic plane compared to those stars far from the galactic plane. Now, if we divided the same dataset in several latitudinal strips, what we have is that the metallicity distributions are correspondingly having this shape. So the colors are corresponding to this folded version of the strips. So what we see here is that the distribution of the stars is a bit more complex. We need 3 Gaussian components to fully explain the distribution of stars. But overall, we have similar properties comparing to the optical. So the position of the component seems to be fixed independently of the latitude, while the proportion of metal-rich stars is larger here close to the midplane than far from the midplane where metal-poor stars are more abundant. So qualitatively, the same results we have seen before with optical surveys, but here a bit more detail because of larger samples coming from the Apogee sampling. So when we look to the kinematics, and here I'm doing it in the context of the 3 components suggested here, we see that metal-rich, metal-intermediate, and metal-poor stars display different kinematics. So we have for all of them cylindrical rotation, independent of the metallicity, which is also consistent overall with what we see in external galaxies, such as this one from Gonzalez et al. 2016, which is a hint of cylindrical rotation coming from secular evolution, producing those structures. But we see some difference between metal-rich and other stars in the sense that there is a stronger rotation close to the midplane for metal-rich stars compared to the other 2 metallicities. And overall, a slower rotation for metal-poor stars compared to metal-rich stars. We can see this also with those rotation curves, where we see that clearly the rotation is steeper for metal-rich stars compared to metal-poor stars, for example. We can look instead to the galactocentric velocity dispersion maps. So here, each pixel is the dispersion of velocity of stars corresponding to metal-rich, metal-intermediate, and metal-poor components. So we see overall that there is a central enhancement for metal-rich stars, where the variation is more vertical than others. And you see that vertically the kinematic becomes colder. But instead, for the more metal-poor populations, they have an overall higher velocity dispersion all over the bulge area. And the variation, if there is some variation, is mostly radial rather than vertical. We can see again the things here with velocity curves, where for metal-rich stars, we see the central enhancement towards the midplane and towards the minor axis. While for metal-poor stars, there is a much flatter and kinematically hot profiles. Coming back to chemistry, when we include the alpha abundance dimension, so concerning here metallicity versus, for example, magnesium here over iron, we see that bulge stars display a sequence but overall a bimodal sequence where we see clearly that metal-rich stars separate from metal-poor stars. And this has been shown here as in this plot from data from the data release 14 from Apogee, but recently confirmed from analysis of larger samples from data release 16 of Apogee. But coming back to optical surveys, here data from the Gaia ISO, when we compare the bulge track, so here the black points, compared to the trends of thick disk and thin disk, we have some qualitative comparisons in the sense that thick disk stars here represented by the red profile, they are quite consistent in the locus with the bulge stars, especially for the less than solar abundance metallicity stars. But when we compare with the thin disk, they are more consistent with the most metal-rich stars in the bulge. This is in a qualitative sense. So it seems that metal-poor bulge stars can be associated with the thick disk, while metal-rich stars from the bulge with thin disk stars. But when we look at the detail, for example, here the knee of the bulge sequence, which is defined as the point where the sequence breaks down, we have estimated that for bulge, this position happens in metallicity at minus 0.37 dex, while for a local and inner thick disk sample, this happens at a slightly lower metallicity value. So with an overall knee difference in metallicity of 0.07 dex. This is in the border of being statistically significant, but if real, it means that the star formation rate of bulge stars was higher than that characterizing the thick disk stars. So this will be a physical difference between both type of stars. So overall, if we consider all properties, some of them I show you here and others that will be discussed elsewhere in this conference, we have a dichotomy between metal-rich and metal-poor stars, in the sense that for metal-rich bulge stars, we have that they are dominant close to the midplane, so they trace something that can be associated with the bar. Also because they display a double red clump, something that I didn't show here, but that reveals a three-dimensional X-shaped distribution. They have bar-like kinematics, as I showed you before, and they are chemically similar to the thin disk overall. And they are young and old, considering some studies concerning ages. When we look instead for the metal-poor bulge, we find that they are dominant far from the midplane. Let's say they are more uniformly distributed over the bulge area. They do not display the red clump, which also say that they have a more isotropic distribution, but they also have a more isotropic and kinematically hot kinematics over all the region. As I mentioned before, they also have a knee in the sequence of alpha versus metallicity, which happens at a slightly higher metallicity with respect to the disk stars. So they have also a difference in that sense. Something that I didn't say before, that also according to recent studies, the overall alpha abundance of bulge stars might be slightly higher than that corresponding to thick disk stars at the same metallicity. As I mentioned, metal-poor bulge stars display also kinematic rotation, which is something that can be associated with secular evolution, but they are overall old. So trying to summarize here concerning the question about what this tells us about the evolution of a galactic bulge, we can say first that the Milky Way bulge is a complex region with at least two different structures of populations. And this implies the potential concurrence of multiple mechanisms or origins to explain the assembling of the bulge. So we need internal and possibly we need also external mechanisms. As I told you before, when we look at metal-rich stars, they seem to be associated with the bar, and so with a secular formation origin, maybe related with the early thin disk of the Milky Way. But when we look to metal-poor stars, they seem to be not necessarily associated with the galactic bar, and there is not currently a clear mechanism associated to them. So there are several suggestions you will hear about in this conference. So merger or in situ early vigorous star formation in gas-rich environment. So something that we can see in galaxies at high redshift, and I also expect to hear about that in this conference. Or maybe the secular evolution of the tip disk. There are several alternatives, and there is not a common agreement about that. So, well, I would like to stop here, and I will be happy to take questions and discuss about all of this in Slack. So thank you for listening to this talk, and see you on Slack.